I'm Nick, and I build informatics tools in R, and we typically work with genomic data. And I'm going to try and tell a story about how we leveraged the grid to do some pretty interesting stuff that was somewhat novel. So I'm going to start by kind of making sure that everybody's up to speed with some of the basic biology of that. Oops. Okay, sorry, I went ahead too fast. So just so everybody kind of knows where we are, when we talk about biological data, we're typically talking about genomes, and you can really just think of genomes as large strings of nucleotides, so HTCG, repeated all over again in all sorts of patterns. And when you have something novel, like a novel genome, it's relatively easy to predict where genes are in that genome. Stops are a very hard clear signal, and starts have very, very conserved clear signals across almost all domains of life. So if you cultured something brand new and you sequenced it and assembled it, and you have this big novel genome, you know where genes are. But predicting what genes do is actually pretty difficult. And we're interested in that task for a lot of reasons. And so we wanted to build a tool that did prediction pretty well. And if you're in the field of biological bioinformatics or computational genomics or whatever you'd like to call it, that probably just sounds like annotation to you, and that's all it is. If you're not in the field, this might sound a little bit like classification. They basically are just two things for the same task. And this is just the task of taking a novel gene sequence and assigning a function to it based off of a library of sequences that you have, so your training data, that have known functions attached to them. So you want to give a novel sequence a descriptive and succinct label that describes that sequence's job or function within a biological system. So in kind of a cartoon schematic, this just looks a little bit like this. You start with these like text strings essentially that are amino acid sequences, and you try and figure out, does my new thing have a function represented in my library? So this is just classification, nothing crazy fancy. So typically this is done now with tools like Hammer and Blast for good reason. They have pretty clear effectiveness in that, but they tend to suffer from this problem that's considered annotation creep. So we wanted to deal with that a little bit. So we built a classifier that we wanted to emphasize conservative classification with. And this is sort of the setup for how we use the grid. So we built this tool. It's in review now. We have reviewer comments to respond to. So we're pretty hoping it gets published soon. And none of the work we did to build this would have been possible without the grid. That's sort of our big emphasis. So we worked with a whole bunch of data. So our data preparation had to be done on the grid. Our parameter tuning had to be done on the grid. Our cross-validation had to be done on the grid. We tested various iterations of this tool on the grid before we submitted this paper. Absolutely nothing we did could have been done without having access to high throughput computing. So I'm going to try and delve a little bit into a piece of the construction of this that's in our parameter tuning called K-mer matching. So I'm going to introduce that in a second, but sorry. So this is just a figure from the paper that we're trying to publish. And that you can think of this as a kind of a cousin to an ROC curve. This is a misclassification over classification curve. And this is just sort of how you benchmark a tool like this. It's not as simple as a yes/no classifier. You can be wrong in multiple ways, and so you have to be able to understand your error rates in the many ways that you can be wrong. So there's one last little bit of biology that I'd like to make sure that I introduce before we talk into how we use the grid. And that's that the tool that we built works under this concept called K-mer matching. So this is the idea that if I have a sequence, if I have two different sequences and they share a large substring of letters, that there is an implied significance between that sharing of that substring of size k. So that implied significance changes based on what k is. So a string of a 5-mer being shared between two sequences may not be that interesting, but maybe a 10-mer is, or a 20-mer, or a size that's dependent upon the eventual lengths of the two sequences themselves. And that's the basis for our tool. And we built our classifier. It worked really well, and we knew about this interesting concept, that exists in computational biology called reduced amino acid alphabets. And this is sort of the idea that amino acids side chains can represent very, very similar information to one another when they're similar chemical entities. And so we wanted to know if these substrings that are being matched had very small or fine deviations from one another. Could we use that to improve the recall of our classification without our precision suffering? So if there was a little bit of flexibility in our k-mer, did we find the right thing more often while not picking up errors in our classifying? So okay. So we, the insider baseball was that we knew that that reduced amino acid alphabets could help a lot. They pre-exist us. We tested some from other sort of subfields, and we found that they provided an improvement to our classifier, and we tested others that we expected to provide an improvement as well, and it turned out that they didn't. They actually made our classifier worse. And so we had this sort of task in front of us where we knew we could build a big improvement into what we were doing, but we didn't quite know how to correctly tune this parameter. And the brute force way of tuning this parameter is sort of shown in like a cartoon schematic like this. You start with your 20-letter amino acid alphabet. If you remember your biology, you might say, oh, isoleucine and leucine are two very similar side chains. They might be able to represent the same bit of information. If I make them represent the same bit of information, I can test a 19-letter alphabet and see how that alphabet performs in the classifier. And if it in fact does improve the classifier's performance, I can then sort of generate more progeny alphabets. So a similar thing can be sort of thought of between serine and threonine, which are aliphatic hydroxyl groups. So they act as hydrogen bond donor acceptors, or they can be phosphorylated. So they can perform very similar jobs. So the task here is finding where condensing your alphabet gives you access to more k-mers in your testing, but does not obfuscate information more. So another sort of cartoon schematic of this could be looked at like this. So you start with one 20-letter amino acid alphabet, and you have 190 size 19 amino acid alphabets to test. And then it turns out that you have 15,000 size 18. So these would be alphabets with 2 reductions in them. And then you can actually calculate how many you have at every level. So every sort of binned by size levels of alphabets. And it turns out that this is 51 trillion possible alphabets. So we know that we have this concept that helps us improve classification. There are pieces of literature that we expected to help and didn't, and others that we expected to help and did. And we have to figure out what the best reduced alphabet for our classifier is. And even though the grid is fantastic, we probably don't want to test all 51 trillion alphabets. That's, first of all, we'd like to remain in the good graces of the OSG. And second of all, a large portion of those alphabets are probably quite bad. So there's a large portion of that search space that you should sort of know ahead of time. It would not be quite helpful to you. So the problem looks a little bit like this. So we have all these alphabets. We can sort of iterate down through them by their sizes. And it turns out that we can attach statistics to alphabets after they've been tested to say whether this improved or didn't improve the classifier. And then we can only select alphabets who improved classification to produce progeny alphabets at the next level. And this is a process that just repeats over and over again until you get to sort of the smallest level alphabets that you can test. And if this sounds a little bit like a DAG to you, that's what it was. We used a rather straightforward DAG. I believe that Lauren called it a shish kebab to do this. And there were a couple of things about this DAG that we really thought were pretty fun when we were building it. And the first is that all of these jobs have relatively trivial requirements: 1 CPU, 1 gig disk, a couple gigs of RAM. Even though we were doing a whole lot of jobs, this was really nice for us. We were able to get a lot of nodes at one time. And the other thing that was really cool to us when we wrote this is that we obviously can't see ahead in the DAG to predict how big each level will be. So as each level ends, it ends up with a postscript that rewrites the next level ahead of it to take in certain data to change the size of the jobs that it's going to request and things like that. So we used sort of a big fire and forget job to do all of this testing, and that was really quite fun for us. It took a little bit of tuning, but we were able to get it. And that's really sort of the power of the grid to us. So we had a task that had sort of a lot of dynamics to it that we didn't particularly want to manage by hand. As I said, we submitted this and it just ran, and eventually we got our answers from it, which was really nice. And the output of this job looks a little bit like this. This is a figure from our paper that is hopefully soon to be published, where the line represents the sort of performance of the standard amino acid alphabet in our classifier. And each sort of vertical group is a group based on sizes of reduced alphabets. And each point represents a unique reduced alphabet that was tested. And as sort of the trend that you see is that as we get a little bit smaller, we start to get a little bit better. And then sort of so the 19s are a little bit better than the standard amino alphabet, but many are worse. The 18s, a few are better, many are worse, and so on and so forth until we get down to the point where we eventually start to get alphabets that are worse than the standard, and then much worse at the very, very end of our DAG. So this was really cool to us. We had no idea how many alphabets we would eventually test. It turned out that we only tested about 500,000, which was, we weren't quite sure to expect that, but that was sort of interesting to us. But it also sort of helped us for our goal of avoiding an enormous amount of test space that we didn't need to look at. So that is our really brief story about how the grid helped us perform something that was really interesting. We built a tool, we had an idea, and then we used the grid to help make our tool a little bit better. And that's pretty much that. So there are a lot of people to acknowledge here. My boss, Eric Wright, was sort of the entry point to my work in the grid. He worked with it when he was at Wisconsin. My group sort of listens to me talk about this all the time. I was funded by the NIH under a training grant, and then I'm now funded under a DP2. I attended the OSG user school, which was wonderful. I cannot plug it enough. And then the people at the OSG who answer all of my sometimes very interesting emails, they have been great, and they've helped us do some pretty cool stuff. And that is, I went a little bit faster than I expected, but I think that's probably fine given that questions are good. So that's my talk. I'm going to stop my screen share and I can take any questions.